Welcome to this explainer, where we are diving headfirst into what might just be the ultimate mathematical cold case. A remarkably clean mathematical identity that honestly might have been hiding in plain sight since the 19th century. Today, we're unpacking a really fascinating new candidate manuscript released by Evidence Press. They're calling it the degree difference principle. It's this elegant, exact identity that is absolutely already making waves, mainly because it sits right in the middle of territory algebraic geometers have literally been mining for over 100 years.
So the big question we're investigating today is, did we somehow miss a genuinely fundamental rule for an entire century? Or did someone back in the 1800s actually find it first? Because if an identity this elementary and this flawless is truly brand new, it completely changes how we approach some of the oldest questions in geometry. But, if it turns out it's already buried in some dusty 19th century textbook on elimination theory, then we are looking at one of the most thrilling rediscoveries in modern mathematics. Okay, here's our quick roadmap for today. First, we'll look at the beautiful discovery itself. Second, we're deconstructing the math. Third, the century-old target it aims at. Fourth, the boundary of human versus machine proof. And finally, the unsolved mysteries left for the community to tackle.
All right, let's jump right into part one, the beautiful discovery, the degree difference principle.
It is incredibly rare in higher mathematics to find a closed-form identity that you can essentially read out loud in a single breath, but that is exactly what the authors of this paper, attributed to OpenAI Codex and Anthropic models, by the way, have presented to us. Just look at this deceptively simple equation on the screen. It is literally just the difference of 2 degrees multiplied by the square of the resultant. More formally, the manuscript proves that a specific Jacobian determinant evaluates exactly to the difference in degrees between 2 polynomials, represented here by r minus s, multiplied by their squared resultant with an alternating sign in front. That's it. There are no extra messy variables, nothing else survives the calculation.
Now, as we all know, the resultant zeroes out exactly when 2 polynomials share a root. But in the context of this new manuscript, that classical property is being leveraged to perfectly balance the entire equation. Rather than just acting as a simple root checker, the resultant squared value actually anchors the whole identity, effectively collapsing all those polynomial complexities into a single definitive algebraic state.
Moving on to Section 2, deconstructing the math behind multiplying and finding roots.
Think about the setup here. The authors construct this combined mathematical map where you feed in 2 distinct polynomials as your inputs, and your output is dual. You get their multiplied product right alongside the resultant.
And here is where the magic happens. When we calculate the Jacobian determinant, which remember measures exactly how this specific map stretches volume, a minor mathematical miracle occurs. All that messy algebra perfectly cancels out. It collapses entirely into our ultra-clean degree difference equation. The complex interplay of those dual operations just funnels down with total mathematical inevitability into this one precise formula.
So, what this actually means structurally is that this map's volume breaks down exactly where the 2 polynomials share a root, or where their degrees are exactly the same. Think about it. When the resultant is 0, the whole equation becomes 0. When the degrees are equal, meaning r equals s, well, r minus s is 0. So once again, the whole equation zeroes out. Mathematically, the map suddenly becomes degenerate in these highly specific scenarios. It's a gorgeous structural bottleneck that this equation identifies absolutely flawlessly.
Which brings us to Section 3, the century-old target, the Jacobian-conjecture.
You might be wondering, why does a beautifully simple equation about polynomial maps matter so much to modern geometry? Well, it's because this new principle is totally foundational for building geometric slices of factorization spaces. And these spaces act as the exact stage where the massive, unsolved 1939 Jacobian conjecture actually plays out. Proposed by Odd-Henrik Keller, this notorious puzzle has completely frustrated mathematicians for decades because even seemingly straightforward polynomial mappings can harbor these hidden, intractable complexities. It's remained stubbornly open even for just 2 variables. But this newly released degree difference principle from 2026, it sets up the exact geometric scaffolding needed to screen and test behaviors related to Keller's famous puzzle.
The manuscript classifies the absolute simplest of these slices and writes down explicit coordinates for them, identifying obstructions that essentially rule out simple behavior in higher degrees. By isolating these affine slices, mathematicians finally have a structured arena. They have the explicit coordinates necessary to study induced Keller maps. It's honestly like suddenly being handed a highly detailed topological map of a completely uncharted jungle.
All right, Section 4, human versus machine proof and the verification boundary.
Now, how this paper was actually verified by its AI-attributed authors is wild, because it brilliantly illustrates the modern boundary between what a computer script rigorously checks and what relies entirely on unchecked human prose. The evidence package they dropped includes a SymPy Python script that explicitly computes and validates the identity for lower degrees. But, and this is a big but, the general all-degree proof, along with the deep structural theories regarding torsors and divisor classes, rests solely on traditional written prose that hasn't yet been machine-verified or peer-reviewed. It's an incredibly precise, honest snapshot of where the verification boundary lies right now.
And finally, Section 5, Unsolved Mysteries and Next Steps, the call to action.
So what should the mathematical community actually take away from this unrefereed release, and what the heck happens next? Well, the paper essentially hands out a high-stakes to-do list for global experts. Settle the priority question, review the structural half, and mechanize the general identity. These are totally actionable next steps aimed squarely at classical algebraic geometers, researchers of the Jacobian conjecture, and symbolic computation experts.
The absolute most pressing task is bibliographic. Algebraic geometers need to search 19th century elimination theory to see if this exact equation already exists in disguise. Because resultants have been studied so heavily since the 1800s, there's a real chance this clean identity might be hiding in some old German or French manuscript, just written in a different notation. Finding it would obviously recalibrate the whole release, but confirming its absence, that would cement a permanent new result.
On top of that, symbolic computation researchers have a super clear path right now to extend the SymPy checker beyond degree 4. Doing that would elevate this discovery from a checked pattern to a universal proof. The architecture is literally already there. Automating the general degree verification is entirely within the reach of current computer algebra systems, and doing so would permanently bridge that fascinating boundary between human assertion and machine proof that we were just talking about.
To wrap up this explainer, we are basically left with a thrilling mathematical cold case, just waiting to see who or what will solve it first. Will a human mathematician unearth this degree difference principle in a dusty 19th century archive? Or will an AI research agent scrape the historical data and beat us to it? The stage is set, the math is beautiful, and the hunt is officially on.